Today, you plug a charger into a wall without a second thought. But in the late 1800s, electricity was terrifying. People viewed it as a raw, untamed force, highly dangerous and prone to starting deadly fires. Nikola Tesla was a disciplined mechanical and electrical engineer. He spent his days solving a massive logistical puzzle. How do you generate enormous amounts of power, move it miles across the country, and make it safe enough for a family living room? At the time, the standard was direct current, or DC. Think of DC like a river flowing steadily in one direction. It is incredibly strong right next to the power plant, but as it travels, it loses pressure. To power an entire city with DC, you would need a loud, coal-burning generator on almost every corner. Tesla's solution was alternating current, or AC. Look at this animation comparing the two. At the top, that straight line is direct current, fading out rapidly over a short distance. Below it is AC. Instead of a steady forward flow, AC works on a push-pull mechanism. That continuous wave maintains its strength, allowing it to travel vastly further without dying out. Alternating current provided a delivery system that made nationwide power grids physically and economically possible. Alternating current is unique because of how the power behaves while it is moving. This diagram shows exactly how it works. Because the current is constantly switching directions, engineers can use transformers to massively increase the pressure, what we call voltage. That sudden expansion you see allows the electricity to sprint across hundreds of miles of wire in an instant. But you cannot have ultra-high voltage bursting out of your living room wall. So, as you can see here, once that power reaches its destination, it gets stepped down. The tall wave compresses back into a small, gentle current that is perfectly safe to run your lamps and appliances. To use this alternating power to do physical work, Tesla invented the polyphase induction motor. This design works like several hands spinning a wheel in a smooth circle, running with much more efficiency than previous engines. With the motor and the AC system in place, the scale of power generation exploded. Engineers could now harness massive, remote natural forces, like the heavy water flow at Niagara Falls, and convert that kinetic energy into electricity, sending it to cities miles away. Stepping power up for the journey and stepping it down at the destination, Tesla's system saved mountains of coal and thousands of miles of wire, solving the geographic limits of power. Once the baseline AC system was up and running, Tesla's engineering mindset took over. He wanted to see what happens when he pushed the system to its absolute physical limits. He started experimenting with high-frequency currents. Standard AC power, the kind in your wall, pushes and pulls 60 times a second. Tesla began designing circuits that alternated 100,000 times a second. To test these extreme frequencies, he built a highly specialized diagnostic tool known today as the Tesla coil. He immediately ran into a public relations problem. Generating high-voltage, high-frequency electricity snaps loudly in the air and produces massive, blinding sparks. To the public, it looked completely lethal. Inventing the technology was only half the battle. Tesla realized he had to devise a way to overcome that human terror and prove his extreme frequencies were actually safe and controllable. Tesla's solution to this PR problem was extreme. He decided to step onto public stages and use his own body as the electrical conductor. During highly publicized lectures at massive venues like the 1893 World's Fair, he would pass hundreds of thousands of volts through his own chest, using his bare hands to light up a glass bulb. He survived these massive shocks because of a physics principle known as the skin effect. This anatomical diagram illustrates how the skin effect works. When you encounter electricity at ultra-high frequencies, the current travels exclusively along the outer perimeter, the skin of a conductor. Those glowing lines show how the electricity flows completely over the outside of the body, bypassing the heart and internal organs entirely. These public displays were carefully calculated live engineering demonstrations. He designed them specifically to prove that the physics of high-frequency currents were entirely sound and perfectly safe. In 1894, all of this rigorous work was compiled into a technical volume titled The Inventions, Researches, and Writings of Nikola Tesla. This was a detailed manual meticulously recording the math and mechanics behind his polyphase motors, his high-potential lighting systems, and those famous stage lectures. Because of its deep practicality and clear data, this book became the definitive text for an entire generation of practicing electrical engineers. The principles laid out in those pages are exactly what powers the screen you are watching this video on right now. His extreme experiments with high-frequency coils laid the direct groundwork for neon lighting, early radio transmission, and the wireless technology we use every day. Tesla was a disciplined engineer working in a rigorous laboratory environment, surrounded by tools, messy workbenches, and hard data. Tesla built the practical systems that distribute electricity to almost every home on Earth, and then stood on stage, using his own body to prove to a terrified public that it was safe.